Hey everyone, this is Matt with Learn Everything About Design, and in today's video, we're going to be doing some thermoforming of our 3D printed parts. And so this idea came along to me. Somebody sent me a video of Zion Brock's AM radio build. If you haven't seen that, I'll leave a link in the description of the video. It's a really cool idea, a really clean design that he's got. Obviously, it's all 3D printed. And it inspired me to build my own for a relative that I have. And so I'm gonna be doing that. Maybe we'll do some videos on it on the channel, I don't know. We won't be copying his design, but again, we will give credit where credit's due. I love the idea behind a simplified sort of MP3 player radio and the techniques that he's used on his. And so we'll talk about that in the future. But again, for this idea, it did come from his video. And so if you want to check it out, what he's learned, his process, then make sure you go to the description of this video after you watch it and then check it out. All right, so for this video, what we're going to talk about is what you need to make this happen and some of the things that I found along the way that worked and didn't work. So first things first, what do you need? Well, obviously some CAD program. We use Fusion or Plasticity or SolidWorks or Blender. Pretty much any of these are going to work fine. The second thing you're going to need is a 3D printer, obviously. For these, all these parts were printed on the Bamboo Labs P1S. Could use pretty much any printer. I'm just using PLA. Most of these are PLA Plus tough. One of these, I think the green one, is just basic PLA. They pretty much behave the same, not too much difference for what we're doing here. Now, obviously, if you go to a PETG or an ABS or something like that, you have slightly different transition temperatures. You have to deal with some potential off-gassing, things like that. Make sure that you think about all these things and you use your own safety precautions whenever you're trying to heat up plastic in your garage. All right. The second thing that you want to make sure you have is a heat gun. Now, it's not going to work with like a hair dryer. You're going to need something that gets pretty hot. Most heat guns for things like heat shrink for electrical wiring and soldering, they're going to be somewhere in the 600 to 700 degree Fahrenheit range, more than enough to get this plastic up to its transition temperature relatively quickly. When we're talking about printing infill, especially if we're using fairly sparse, like 5 to 15%, you're talking about really thin plastic, and that thin plastic will heat up quickly. And so you do need to have something that has that heat range on it, but just keep in mind that it doesn't take much. It will happen relatively quickly. PLA like this could be heated up with like boiling water and steam if you really wanted to. There are other ways that you could get about it, but a heat gun that's meant for things like shrink wrap is really the quickest way. All right, with that, the next step is to actually design your shape. Now you will have to design parts flat. This can be tricky. In some cases, so I have an example that we'll look at in a little bit. I used sheet metal and I designed a little bracket, and then I used a form to sort of bend it into place. That's one way that we can do it. It's a little bit trickier because we can't bend the part right on a bend line. If you do have a positive and a negative form with an appropriate amount of gap, then you can make that happen. For these parts, what we're doing is using a mechanical force rather than the traditional vacuum or pressure that you see with thermoforming. So what we need is some way to hold this part, and then we also need a form or a shape to pull it down on. Now, I've got a couple here. I played around with different thicknesses or different heights, which is really the depth that we're drawing the plastic. And I found that my own parts kind of work best in the roughly 2 to 2.5 times the thickness for how deep you can pull them down. Past that, they start to really stretch a lot on the sides, and you start to get breakage depending on the infill that you're using. And so for my own testing, my own purposes, I found that 2.5 to 3 times the thickness of your part is really where that sweet spot was. You can go deeper. It's going to depend on your infill. For me, again, I just kind of found that was the limit. Next, let's talk about the infill. Now, the infill, for the most part, you can use anything you want. But for my own testing, I found that 3D style infills like a gyroid or a 3D honeycomb really gave me the best results. Structurally, they're much stronger, and they allowed me to kind of get away from any potential issues that we have on the corners. And so this part here, which we'll look at in just a bit, was just a 2D style infill, which means that it's just being built vertically up in Z. And it really doesn't have a lot of connection around the rim. And so it started to deform and break relatively quickly. The same sort of infill amount in a 3D style of the same infill in this case worked much better, much stronger. It handled the deformation better, and better connection to the outside of our part. And so that's something to keep in mind. Not all infills will work the same. Ones that are 2D, especially as you get lower in the infill amount, so 5, 10, 15%, they will really stretch and you'll probably have some breakage around the outside. As you get higher up in that number, 30, 40, 50% infill, then what you're going to see is a deformation in the negative space. So if you use something like a honeycomb, you'll see around the edges, it's really going to start to stretch and you'll get elongated sections. And so for my purposes, I've played around with just the standard honeycomb. I got some good results with it, but what I didn't like was how much the honeycomb actually sort of deformed and how you could tell. So that's not what you would expect to see in something like a speaker grate, for example. So going with the 3D infills, whether it's a 3D honeycomb, the gyroid, or some of the other style 3D infills, those really gave me much better results. Now, the thicknesses that I played around with for my part, I made the lips or the rims around the outside. I made those 5 millimeters, and then the section where I wanted the infill, I made that 4 millimeters, and that worked best for me. I went thinner than that, and I saw a lot of deformation and stretching and breaking in the corners. And so that was, again, my sweet spot. 4 millimeter thick on the area I wanted to form, a 3D infill, and roughly 2.5 to 3 times the thickness of that part for the overall deformation or that stretch that we're trying to get. It's also important to design your form. You want to have a part that you can hold the sort of the blank in, something that you can use the heat gun and not get it directly on your hands, or of course wear some gloves if you're going to be anywhere near blowing that on your hands. Even in the garage, which is 40, 45 degrees right now, which is really cold, that was still very hot. You know, 600, 700 degree temperature is extreme for blowing it right on your skin. But having something that you can hold your parts in, that really helps. It goes a long way. And then when you're designing a form to pull it down over, having some sort of register mark. In this case, I have these little sort of just extrusions on the outside that allow me to make it concentric, because in this case it's just a circle or a dome. If it's not a shape like this, it's a circle. If it's more organic, then you will have to have something that you can really use to lock those pieces together. That will help. Otherwise, you're going to end up really stretching it down on one side and potentially causing breakages. All right. The other thing that I found is when I'm preparing these parts, the outside portion, the lip that's going to be held into this thing, really works well if you split that away from the rest of the body. So the area that you want infill, you'll export it or you send it to your print slicer as a single object, a single STL, and then break it into parts or objects. I'm using Bamboo Slicer. If you break it into parts, it'll keep them combined together. So if you move one, they'll both move together. If you break it to objects, they'll be independent and you could accidentally sort of misalign them. So I would suggest leaving them as parts, which is what Bamboo Slicer and some of the others call them. And so with that allows you to control the infill. You can get rid of the top and bottom layer and control the density of the infill of just the piece where you want the mesh. And then on the outside piece, you can make it solid. You can make sure that you've got top and bottom layers. You can do whatever you need to make that happen. And so there's all kinds of different ways that you can go about this, but I found that that was probably the strongest way to do it, was to separate the rim or the locking feature that we want for the outside of the part, and then the infill area, and just kind of break those up as their own bodies. And so the process of doing this is fairly straightforward. What we want to do is use the heat gun, and we want to heat the plastic up. Now I tend to prefer heating the inside up and then flipping it over and heating the outside. Transition temperature happens really quickly on these parts, especially if you have a very thin or a sparse infill. You can get this up to temperature within a minute, like in probably 15 to 20 seconds, really quickly. So be aware that this happens really quickly. You could design a setup where you just use weight and set weight on top of it, and then you can heat it up. But the more heat you put on your actual form, the more deformation you're going to cause in it, because these will ultimately have infill in them. So as soon as you start to heat these up, they will start to deform and have potential problems as well. Now remember, we're deforming this over the inside of our shape. And so if you've got a final shape or size in mind, then that's something that you can use to your advantage. But make sure that you keep your inside walls drafted and rounded. You don't really want any sharp corners. You don't really want vertical walls. The more gradual the transitions can be, the better chance you're going to have at getting these parts out without stretching and deforming them and having breakages. And so the last thing that I want to say, again, is consider designing flat parts, maybe of sheet metal, and things that can be formed. Now, there are a couple reasons that we might do this. One is because of print time. So printing something flat on the build plate, in this case of these little brackets, can take 3 to 4 minutes. Printing it as its final shape on its side, it's going to take 12 minutes. So on one tiny little example, we could save, you know, in this case, a third of the time or 2/3 of the time. And so that can really add up if you're printing 10 of them or dozens of these things. You will have to add in the time to form them, but if you make a jig and you make some way that you can do this, you can really get a little bit more of an efficient process. With Zion Brock's example, I'm going to get off the top of my head here, but I think the speaker grill, he said it was like a 7-hour print with a ton of support on the inside, and it was down to about an hour printed flat, and then of course you have to form it. But that is a massive change in how much time it takes to print a part. So printing it 3D, if it's going to be 7 hours versus 1 hour to print it flat, and then, you know, a minute or two to form it, that's a huge time savings. Not only in just print time, but also material. All the support material is just tossed, and this way there's really no support. It's just printed out flat. You do lose a little bit of flexibility in the design. If you're using something like Rhino and you're using Grasshopper to create the infill, or you know, the mesh design, or if you're using the design extension in Fusion and you're using the geometric pattern, then you can still do that and still form it. This is really beneficial if you're using the infill method in your slicer. So with all that said, hopefully this helps you out. This is a really cool process. There's a lot of applications that I can see it being used on. These parts specifically could be used as little decorative pieces over air filters, or in all kinds of designs, little speaker grates if you're, you know, designing your own speakers for inside of your car, or vent covers or things like that. There's all kinds of different reasons why you might want to do this. And it is much easier to print all these things flat than to have to print them in 3D. Because if you're printing them in 3D, then you're also designing all of this intricate sort of infill or lattice work on the inside. And that's a very difficult thing to do unless you've got the tools to make that happen. So if you have any questions on this, please let me know. Again, I'll leave a link to Zion Brock's radio build, his video, in the description of this one. If you want to check it out, then go on over to his channel and check it out. And again, any questions, comments, leave them on this video. As always, thanks for watching. We'll see you in the next one. Just a quick note, while editing this video, during the thermoforming process, I was narrating the entire time. So I decided to just leave that narration in at the end. So all the information that you've heard in the first part of this video will take care of everything that you need to know. But if you want to get a little bit more in terms of the going through the process, I'll just go ahead and leave it here at the end, and you can watch it if you want. Once we turn the hot air gun on, it's going to get pretty loud, but the first thing that we want to do is figure out how deep we're going to draw the part. Now, as I mentioned, the tighter the infill, and so if we've got a higher density, in this case, this is going to be 20% on just the standard honeycomb. This one can actually draw down a bit deeper, probably not the full 17 millimeters in this case, which was 4x. So I'm going to do the 3x one for this, but it will still stretch out the opening. So that's something to keep in mind. So first step is to pop it in. And again, the way this was designed, just printed exactly the same size. It holds it really well. It's not going to accidentally come out. You have to really force it. And once it's in there, what I like to do is turn the heat gun on. I'm going to heat the back side, and then I'm going to heat the front side. And then once I get it close to that transition temperature, we'll pop it in here. Again, there's a little walls here to kind of keep it concentric. And then I'll go ahead and add a little bit more heat and then push it down. All right, so the next bit of this is not to rush it. And what I mean by that is when this is still warm, you want to let it cool off a bit in here. Now it's 45 degrees in my garage. It's really cold in here, so I don't have to wait very long, but you may want to blow air on it. Now again, this was 3 times the thickness, and so this was roughly 3 times. It's a little bit off from that. So it's still a bit much. I think 2 to 2.5 is really that sweet spot. And what you can see, and I'll go ahead and pull this off, is there's actually some peeling that happens right along the edge. Now it's not all the way around. On this side, it actually works out pretty well. And this thing was concentric based on the shape. And so this is somewhat of a product of where the heat was. I could have heated up this other side a bit more. This side probably got a little bit hotter. And the other thing is going to be basically the orientation of those hexagons, or in the honeycomb. So sometimes, just based on the way that the infill works, you're going to get a different orientation, which puts a really thin section just on one side. But overall, that still works pretty well. So let's try a couple more. Next, I'm going to go to basically a sparser honeycomb. And so this one, I believe, was 10% infill. So once again, pop it up. The actual ring around this part, I made it 5 millimeters, and then the center is 4 millimeters. So it's just a little bit taller. That way I can get in there. This sort of holder piece could be a bit thicker. We could also just set weights on it and use the weights. But I'm going to go ahead and follow the same process here. So I probably should have used the 2.5 instead of the 3 for this one. One of the issues that we have with these types of deformations is really in the fact that the stuff in the center can't spread out. And so you end up with all of the deformation happening around the outside. And so again, we need to let it cool. You can blow on it, you can have a fan on it. It's cold in here, so it's not too bad. But what we're going to see again, like the other one, is we're going to start to get that stretching and that deformation right around the edges. And once again, this is a 2D style infill, which means that it's just building up in the Z direction. And for me, I don't think that that's the best. I think using a 3D style infill, unless it's extremely dense, is the way to go. The amount of heat that you put on the entire form, so while it's in here, if you're blowing down on it, that can cause the parts to stick together because you end up getting the transition temperature of the same material. You could use a different material for the form. Because this is a ring, we can just twist it a little bit, and that will break the pieces apart. And so not too bad, but again, not perfect. I don't really like the way that it was around the outside. So I'm going to switch over to the thinner one. So this one is 10 millimeters tall, which is roughly 2.5 times the thickness, because, well, in this case, it'll be exactly 2.5 times the thickness. And then we'll try another one. And so this time what I'm going to do is go to, I think this was 10%. This is a 3D style of infill. So this is I believe this was the 3D honeycomb. So once again, we'll pop it in. And because of the thin nature of the honeycomb infill, because of the nature of the honeycomb infill, this is actually going to heat up really quickly. So I'm only going to heat it up from the top side. And so once again, that 2.5 is the sweet spot. I'll let that cool off a little bit. And then while that's cooling off, should pop right off. There we go. So this one worked out a little bit better. Again, I think the 3D style infill is the best option. It tends to be a little bit stronger. It handles the deformation a bit better. Now, obviously I didn't draw it quite as deep as I did on this one. This is 10 mil, this is 13. So yeah, it's something else to keep in mind. All right, we got 3 more here. We've got the another one that's a little bit more dense. I think this is 20, maybe 25%. And then we've got a 2D and a 3D infill that we're going to try, and we'll give both of those a shot. Now let's go ahead and look down at this at a different angle. All right, so same deal. I'm going to pop that in, and we're going to begin heating it up. All right. And it's probably hard to see, but you can kind of see from the heat, the actual holder piece is starting to deform right here. And again, because of the infill, once we get that top layer or the bottom layer up to that transition temperature, it'll just start to sink in. So you do have to be careful. Your hands are around this heat. Since it's so cold, I actually don't mind it. And then again, with these parts, depending on how much heat you put in, you may just need to let them cool off a little bit and twist. Let's go ahead and pull it off from this side. All right, so this is again one of the 3D style. Not too bad, not perfect, but again, it handles the deformation around the corner just a little bit better. I'm gonna switch back to the 2.5. Again, I think this is really the sweet spot, and we'll try one of these 3D styles here. All right, so this triangular one does pretty good because it keeps its structure on top. And then when it starts to stretch over the edges, those vertical walls, they're tapered, but they'll start to sort of lay over on their side and deform, which gives it a really good structure. So let's go ahead and pop that one off. It's probably still a little soft. All right, while that one's cooling, let's go ahead and do this one. And I'll stretch it over this. All right, and I'm not sure if you can see this or not already, but this one kind of broke apart. And so again, that 2D, there's just not enough structure around the outside, and it just stretches past the point because we've only got that sort of single area. And so when we go to, again, these things that are like a gyroid infill, the gyroid infill tends to work pretty well, or a 3D honeycomb. This tends to work pretty well. Has a lot more structure around the outside. In terms of the infill density, typically somewhere in the 15 to 30% range is probably going to be pretty good. So again, 3D infill tends to work pretty well. It has a lot more structure around the outside. Let's see if we can get this off without breaking it. It's not Not much structure on the side. But the 2D infill, again, it just doesn't have the structure on these sides. It just kind of peels apart. And so what I would say is sticking with 3D infill definitely does a better job. Or if you're going to go to a 2D infill, make it pretty dense. Now the other thing that we want to point out is going to be, let's go ahead and slide these over, making little things like these brackets. And so the reason for this is because printing parts flat, one is going to give us a consistent layer, whereas printing parts on this side, the layer is in a different orientation. And so layer orientation is something that we need to consider when we're thinking about printing a part in its final shape versus forming it. The other thing is time. To print this part sideways, not only we're going to have some issues with the holes, but it takes about 12 to 13 minutes. To print it flat is going to take 4 minutes. And so we do have a time savings in terms of printing part flat and then forming it. If we're printing a bunch of these, we can certainly print a lot more flat than we would to print it as its final shape. Now, in this case, the quality is going to be better printed in its final shape, just because I didn't do a very good job with the mold here. But again, pretty much a similar process, just heat it up. And once we're at that transition temperature, we can just push down on a form to get to the final shape. And again, this is a very simple and quick example, but just something that you can keep in mind when you're trying to make different types of parts. If you can print it flat and form it versus printing it in its 3D shape, whether it's having a good clean square opening or a hole pattern or something like that, there's definitely some benefit to doing it this way, either in time savings on the print or potentially just structurally. You may have a better outcome if you print it flat and form it in its shape.